Have you ever stopped and wondered what makes your computer, well, compute? Today, we're pulling back the curtain on programming. We're going to explore those hidden instructions that power our entire digital world and see how we go from just using technology to actually creating it.
Let's just dive right in. I mean, think about it for a second. Every single tap, every click, everything you do on your devices, it's all being driven by a set of instructions. Without those instructions, your shiny, expensive phone is, well, it's just a really nice-looking paperweight.
Okay, so to really get our heads around programming, we first need to understand that the software you use every day actually lives in two totally distinct, kind of hidden worlds. They have to work together, but their jobs are completely different.
You know, a great way to think about this is like a theater performance. On one side, you've got the system software. That's the silent, absolutely essential stage crew working behind the scenes, making sure the lights work and the curtains open. And then, on the other side, you have the application software. Those are the actors you actually see and interact with on stage. So let's look a little closer at that stage crew. System software is that deep, fundamental layer that makes the physical hardware actually do stuff. It's your operating system, like Windows or Mac OS, and it manages everything from memory to your printer. It really is the unseen engine that makes everything else possible. And that brings us to the stars of the show, application software. Yeah, this is what you probably think of when you hear the word program or app. These are the tools in your digital toolbox, the things built to do specific tasks for you, like browsing the web with Chrome or editing a picture in Photoshop. All right, so here's the big question. We've got these two worlds of software, right? But how do we get them to talk to the machine itself? How does a human idea turn into an action on a computer?
So, if you could somehow crack open the mind of a computer, what would you find? What language is it really speaking? I can tell you it's not English or any other language you'd recognize. It's something way, way more basic.
It's this, a long, long stream of ones and zeros. That is the computer's native language. It's called binary, and every single digit just represents a tiny electronic switch being either on or off, and that's it. At its absolute core, this is the only thing a computer truly gets. And that, right there, creates a huge problem. There's this massive communication gap between our complex, nuanced human thoughts and the computer's incredibly simple on or off language. We can't just tell it what to do in English. It would have no idea what we're talking about. So, how do we bridge this enormous gap? How do we get from human ideas to raw machine language? Well, we need a translator. And that translator, that's the whole point of programming.
So you can think of programming as the art of writing a super, super precise recipe. We create this perfect sequence of instructions using a special language, one that can eventually be translated for the computer to follow step by step without any mistakes.
And writing that recipe, it's not just about banging away on a keyboard. It's a really structured process. First, you have to analyze the problem. You have to really get what you're trying to solve. Then you abstract it, thinking through examples and logic. Only then do you start to formulate the instructions in code. And maybe most importantly, you have to constantly evaluate your work, testing it and fixing all the little errors. It's this cycle of thinking, building, and refining. Okay, so we've written our recipe, what programmers call source code, but how does that text, that stuff we can read, actually turn into something the machine can execute? What's the magic step that happens behind the scenes? Well, that source code needs one of those translators we talked about. And there are two main types. An interpreter is like a live translator at a conference. It reads one line of your code, translates it, and runs it immediately. Then it moves to the next line. It's great for testing things out. A compiler is different. It's more like a book translator. It takes your entire program, the whole thing, and translates it all at once into a separate, super optimized file the computer can run. It takes more work up front, but the result is much, much faster. And this entire journey, from your thought to the computer's action, happens in a flash. You write the source code. A translator, a compiler, or interpreter turns it into machine language. Then, a linker grabs any other little pieces of code it needs and combines everything. And finally, the operating system loads that final program into memory to run. This exact process happens every single time you launch an app. Okay, so that's a pretty clever process, right? But so what? Why does this translation from a human idea to a machine action actually matter so much? What does it empower us to do?
It really boils down to this. This is the whole point. Programming is what transforms a lifeless box of circuits and silicon into a powerful, world-changing tool. The hardware gives you the potential, but it's the program that gives it a purpose.
And with these instructions, with this ability to give purpose to hardware, we can do some absolutely incredible things. We can make computers solve massively complex problems in the real world, from finance to medicine. We build the apps we all have in our pockets. We automate our lives. And we create entire new worlds of art and entertainment.
At the end of the day, a computer isn't smart, not on its own. It's just an incredibly powerful tool that's waiting for instructions. The hardware is just potential, sitting there. The program is the purpose. So the real question isn't what a computer can do, it's what will you instruct it to become.